uploaded in the link will be shared with the NPTEL learners. So, yes, welcome to the ninth session of the problem solving. Uh, um, Welcome to the ninth session of the problem solving weeks. So, for the course Geotechnical Engineering 1, so I'm Yogendra Narayanan. I'm a PMRF research scholar who has been handling these sessions this time and for the past two times. So the course instructor is Professor D.N. Singh and from IIT Bombay. So to give a brief background of this session, these sessions are intended to make the NPTEL learners proficient in the concepts that has been taught in a particular week uh, by making them solve questions based on that content so that they get uh, used to the type of questions that they can expect in the NPTEL exams. Uh, uh, and also it will be useful in tackling their competitive examinations, professional interviews, and university exams also. So, with this introduction, today let us go into this week's problem solving session. So, to give you brief background of this particular session, so it is mainly targeted on the flow nets, how to analyze them and things. And initially, we'll be starting with some of the basic questions, followed by some numericals as well as some uh, derivations. All right. Any
Okay.
doubt?
No, sir.
And you are encouraged to ask questions, get it clarified, get your doubts clarified. You can interrupt me at any time. All right.
Yes, sir.
So, with this, we'll be entering into the session. Right. So, the first question: top flow line in a dam is a what type of curve? Top flow line in a dam is a option A hyperbolic, option B logarithmic, option C parabolic, option D straight line. So, to elaborate this question, so this is a earthen dam. All right. Uh, Let us consider. Sorry, this is the water level. This is the downstream. Right. So, what will be the top flow line usually? How it is? How the top flow line is defined as what? Any idea?
So top flow line और equipotential line perpendicular होता है one और ये equipotential line.
Equipotential line. In this figure, which is the first equipotential line? So flow net consists of both equipotential and uh, flow lines, right?
Yes, sir.
So we, which will be the we are now we are not concentrating on equipotential line, so we are concentrating on a flow line. The topmost flow line in this is what?
Sir, water table level से ये downstream side के connecting.
So this is known as what line? This is defined as what line? So what is the pressure head at 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 this along this line? What is the pressure head along this line?
Atmospheric pressure.
Yeah. So if the line connecting the atmospheric pressure is known as
phreatic line.
phreatic line. So that is the topmost flow line. So the nature of the phreatic line is what type of curve? It is a
Parabolic.
parabolic curve, right? So the phreatic line, which is the top flow line, is always a parabolic curve. Understood?
Yes, sir.
Okay. So any doubts?
No, sir.
Okay. So let us move to the next question. Outcrop point is defined as, among the four options, first is point at which phreatic line cuts the upstream face of the dam. Phreatic line meets the rock toe. Point at which phreatic line cuts the downstream face of the dam. Point at which phreatic line touches the downstream filter. How outcrop point is defined? How outcrop point is defined? So let this be the again. So let me not draw it again. So we will work on this. Let me do it a little bit clumsy. So this is the earthen dam, right? Let us consider this is the earthen dam, and this is the line, and this will be the phreatic, right?
Yes,
So
sir.
this is the phreatic. Let me name it as PL. So which is known as the option A, point at which phreatic line cuts the upstream face of the dam. So that is this point, right? This is A, point at which phreatic line meets the rock toe. So whether if the rock toe phreatic line meets here, this is point B, that is option B. The point at which phreatic line cuts the downstream face of the dam, that is point C. Point at which phreatic line touches the downstream filter. So if there is a filter here, so this touches here. So which is the outcrop point? Any guesses? Any idea?
D. At mid the rock too.
Partially it's right, but the particular definition of outcrop point is where the phreatic line cuts the downstream point. That is option C. So the you this once the phreatic line cuts the downstream point, what happens? So the downstream starts to erode, right? So to
Yes.
avoid that, we place filters at the downstream end. So this outcrop point is pulled towards the filter or rock toe by installing either downstream filters or rock toe filters, right? So uh, as you mentioned, so the options B and D are subsets of option C. So and these are the remedial measures to remove the outcrop point. But the outcrop point as definition is without the presence of any what to say, any filters or external structures, the intersection point of the phreatic line at the downstream end is known as outcrop. Any doubts?
No, sir.
Okay, is it clear? Are you able to follow me? Is my speed fine, or you want to slow down a little?
नहीं सर ठीक है.
ठीक है ना? So for a toe angle alpha less than 90 degree, the velocity of the top flow line at exit is option A at an angle alpha to the downstream phase, perpendicular to the downstream phase, parallel to the downstream phase at an angle 90 minus alpha to the downstream phase. So how will you understand this? So now for you need to understand what is toe angle. Toe angle is this one, alpha, alpha. So for alpha less than or equal to 90, right, the velocity of the top flow line at the exit is, so it comes here, and the top flow line comes and meets here, right? So after this, once it meets the outcrop point, what will be the velocity? How, that means what is the direction of velocity? Any idea? Any idea?
सर नो सर थोड़ा सा क्लियर कर.
So once it comes out of it, so it just follows the slope of the downstream end. So this will be the directional velocity, and this is the normal vector, and this is the velocity vector. So what is the direction of velocity now? Hmm? It is parallel to the downstream phase. So this is the slope of the downstream phase, and the velocity vector is parallel to the downstream phase. Any doubts?
सर कैन यू एक्सप्लेन फिर सर मतलब एक बार और से.
See, this is the flow line, right? So which I have marked it with arrow marks.
यस
So
सर.
once it meets the outcrop point, how the question is a question at the question is asking us to tell the velocity of the that is the based on the given option, they are asking us what will be the angle of the top flow line once it comes out of it. So that is at the out after it crosses the outcrop point. So once it crosses the outcrop point, the velocity will always be parallel to the downstream phase, and the this is the normal vector, and this is the velocity vector, and this is the normal to the velocity vector, right? So the velocity will always be parallel to the downstream phase of the dam uh, once it exits the outcrop point. Any doubt?
नो सर ओके थैंक यू.
For a dam provided with rock flow, the flow at the toe, option A, does not change the direction, enters the flow deviating towards the normal to the interface, enters with flow deviating away from the normal to the interface, bypasses the rock flow. So how does a rock flow filter look? So this is a rock flow filter, right?
यस सर.
and this is the upstream end, the flow at the toe. That is, consider the top flow line. So without the rock toe, the flow line will exit here, right? So with the top flow, what will happen? It will straightly fall into the filter. That means interface is this one. All right. So once you provide rock toe filters, what is happening? It is not at all coming into contact with the interface. That means what it is doing? It is bypassing the rock toe. So not only it bypasses the rock toe, it bypasses the entire downstream phase. So because once you provide the filter, the pressure at air will be equal to the atmospheric pressure. So the flow automatically flows towards the atmospheric pressure, which bypasses the entire downstream end. Understood? Any doubts?
No, sir.
Okay. Shall we go to the next question?
Yes, sir.
Okay. Which of the following is not correct? So for a given set of boundary conditions, the flow net is unique. In a flow net, the flow through all elementary squares is equal. In a flow net, head drop across each channel is equal. Impermeable boundaries are equipotential lines. So how will you analyze this question? So for this, let us consider example. Let us consider a earthen dam, right?
Okay, sir.
Right. So now this is the upstream end. This is the downstream end. Right. So now, since the option contains impermeable boundaries, let us consider the base of the dam is impermeable. All right.
Yes, sir.
Okay. Now this is the top flow line, and this will be the flow line. This will be the again this one, and these are the equipotential lines. Right. So the fundamental what to say conditions of flow net is, for a particular boundary condition, the flow net for each case is always unique. So option A is right. So always the flow net is divided such that it is an elementary square. All right, the sides are always equal. All right, and the Q through all the squares, elementary squares, are all same, because the amount of water that is flowing through this is going to be the same. It is not going to be different. All right. So that is conservation of mass. So that is getting satisfied. In a flow net, head drop across each channel is equal. So that is what we create. So we divide uh, this entire flow net into flow channels, right? So and each flow channel, the total head loss is being equally divided into number of the flow channels. So such that the delta H at each drop or flow channel is equal. So this is the fundamental, these three are the fundamental properties of flow nets. All right, any doubts till now?
No, sir.
Now the impermeable boundaries are equipotential line. So here the catch comes. So as I mentioned, this the bottom uh, part is impermeable in this earthen dam, right? So, but what about which is the last flow line in this? So this is an impermeable boundary, right?
Sir.
So and along this impermeable boundary, let me take it. It goes from here to here. So it is what type of line? It is it a equipotential line or is it a flow line?
Flow line.
It is a flow line. Equipotential line is this line, right? The upstream end of the dam is always equipotential end, because if you keep piezometer here, it will, sorry,
Yeah, the press I had originated.
pressure head is always constant wherever you keep it, right? Wherever you keep it, the pressure head is always constant. And this is the this is a flow line. Even though it is an impermeable boundary, it is a last flow line of this flow net. So that tells us what? Impermeable boundaries need not be always equipotential line. It can also be a flow line. So the statement which is not correct is option
Option B.
D. Any doubts?
No, sir.
Okay. So now coming to this question. So now from now, I think the problem, the numerical part starts. So for a flow across an interface between two soil media of different coefficient of permeability, the entrance angle, that is the incident angle between the flow lines and normal to the interface, alpha 1 is 45°. What will be the angle of exit if the ratio of permeabilities of the two soil media, that is K1 by K2 is root 3? So how will you solve it? First, let us draw a figure. So this is the interface, right? This is soil media 1, soil media 2, right?
Yes, sir.
So the flow line enters like this. Flow line enters like this, and this, let this be the perpendicular line to the interface, and it exits. This angle is alpha 1, and this is it is K1, and it exits at an angle alpha 2, right? And since it is a different media, its permeability is K2. How these two are related? Do you remember the relation?
Yes, sir.
What is the relation? What is the relation?
ratio between two angle is equal to K1 into K2.
K1 by K2 is equal to tan
Angle 1 or alpha 1 or alpha 2. Tan alpha 1, tan alpha 2.
alpha 1 by tan alpha 2. So what is this law similar to? Which law it is resembling? Any idea? Have you come across this type of this type of law which is analogical to something? Hello? Yeah, just a minute, just a minute. There was a uh, small network issue. Is my slide visible now?
Yes, sir.
Okay. So what does this law resemble? Any idea from your past memories? Have you studied optics in your 10th plus 2?
Yes, sir.
So can you remember some law in ray optics where this type of relation comes?
Yes, sir. Angle will be equal.
What is this law? It is Snell's law. So it is also refractive index of 1 by refractive index of 2 is equal to tan incident angle 1 by tan incident angle 2. Right. So this is the law that resembles. So if you are if you find it ever you are feeling some like you are forgetting this, you can always remember this. So now please calculate and let me know what is the angle of exit alpha 2. What is the angle?
90 minus alpha यानी 45.
You use this now. K1 by K2 is different, right? So it is going to be K1 by K2 is what? Root 3. And tan alpha 1 is, see, whatever you are saying, 90 minus alpha is going to be the thing which is when this both mediums are same. When the mediums are different and its properties are different, how can you equate both? So root 3 is equal to tan alpha 1 is going to be 1 and tan alpha 2. So tan alpha 2 is equal to 1 by root 3. What is alpha 2? Tan inverse of
30 degree. Alpha 2 is equal to 30
1 by
degree.
root 3, which is 30 degrees, right? Right? Any doubts?
No, sir.
Right. So now coming to the next question, for a downstream angle alpha is equal to 35 degrees, the total head of 20 meters, the distance from the initiation of phreatic line to the toe of the dam D is 30 meters. What is the distance of outcrop point from the toe of the dam A? All right. So first of all, you have to draw the diagram and depict what has been given in words as pictures, right? So this is the upstream end, right? And this is H, right? Any doubts?
No, sir.
And this is the phreatic line which meets at the outcrop point. So what you need is the distance between the rock toe and the outcrop point is A. So this is what you need. And the second thing what they have given is when you extend this line, distance from the initiation of phreatic line to the toe of the dam. So this has been given. This angle, this line is given, which is how much? 30 meters, which is equal to D. And the toe angle is 35 degree, alpha is equal to 35 degrees. All right. So H is equal to 20 meters. So how will you calculate A? Outcrop point is given by A is equal to D by cos alpha minus root over D square by cos square alpha minus H square by sin square alpha. A is equal to D is 30 by cos 45 minus root over B square 30 square by cos square 45 minus H square is 20 square by sin square 45. How much?
5.42.
Sorry, it is not 45, it is 35. Sorry, please modify it. It's 35. Alpha is 35. How much you are getting?
25.424.
Yeah. So it is approximately A is 25.4 meters. Any doubts?
No, sir.
Okay. Now coming to the next question. A concrete dam is constructed across a river over permeable stratum of soil of limited thickness. The water heads at upstream side 16 meters and 2 meters on the downstream side. The flow net constructed under the dam gives NF equal to 4 and ND is equal to 12. Calculate the seepage loss through the subsoil if the average value of hydraulic conductivity is 6 into 10 power minus 3 centimeter per second horizontally and 3 into 10 power minus 4 centimeter per second vertically. Calculate the exit gradient if the average length of the last field is 0.9 meters. Assuming E is equal to 0.56 and G is equal to 2.65, determine the critical gradient. Comment on the stability of the river bed on the downstream side. So now this question has two parts. Understood? So what are you understanding by the question? Can you briefly explain the question to me? Hello?
Yes, sir.
Can you briefly explain the question to me?
यस सर। कंक्रीट डैम जो कंस्ट्रक्शन है जिसका अपर इन साइड 60 मीटर है और लोअर इन साइड 2 मीटर है।
Hmm. So what is given and what needs to be calculated? You tell that.
कैलकुलेट द सीपेज लॉस कैलकुलेट करना है फर्स्ट पार्ट और कैलकुलेट
It's meant by seepage loss here. Hmm? How will you calculate seepage loss? Let us do it together. All right.
यस
So now initially, first step is draw the diagram. Let this be the ground level. This be the concrete dam. All right.
यस
This is concrete dam. Just to make this switch is simple. So this is the upstream head, and this is the downstream head. What is the upstream head?
16 मीटर
16 meters. Downstream head is
2 मीटर
2 meters. Understood? So this is the existing this one. So now you need to calculate seepage loss, right? So for that, what they are doing is they are constructing a flow net, right? Flow net consists of 4 channels, flow channels, 1, 2, 3, and 4, and 12
यस सर
equipotential lengths, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Any doubts?
No, sir.
So how will you calculate and what has been given? Kx is given as 6 into 10 power minus 3 centimeter per second. Ky is given as 3 into
10 to the power
minus 4 centimeter per second. Convert it into meter per second. How much you will get? 6 into
10 to the power
minus
minus
5 meter per second.
second.
This is 3 into
10 to the power minus 6.
6 meter per second. So what is the formula for seepage loss? Seepage loss is Q. Q is equal to K effective into head difference into NF by
D.
ND. Right? So how will you calculate K effective? How will you calculate K effective?
Permeability
How Kx and Ky are related? Root over
into Ky.
Kx into Ky. How much you are getting?
1.34 into 10 to the power minus 3. Do the x once. 1.34 into 10 to the power minus 5.
So 10 to the power minus 5. What is the unit?
Meter per second.
Meter per.
Meter per second.
Yeah. Now calculate Q. Q is equal to 1.34 to 10 power minus 5 into H is 16 minus 2, which is 14 into NF is 4, ND is 12. How much you are getting?
6.25 into 10 to the power minus 5.
6.25
25 into 10 to the power minus 5.
What is the unit?
Meter cube per second.
Meter cube per second. So calculate it in liter per day.
0.0625 liter per
Liter per, that is per day I'm asking. Liters per day. How much? How much liters per day?
1
Hello?
point
Yeah. Tell me. Hello?
1.264 into 10 to the minus 5 minus 8 liter per day.
Minus 8. How can it be less than 10 power minus 5? Calculate it properly. See, per second it is this much meter cube.
5402 into 88 ja 5402.88 liter per day.
Tell me in English.
5402.88 liter per day.
That is 5,000 liters per day. 5,402 liters per day. So that much is the seepage loss. That much head is getting lost in seepage. Any doubts?
No, sir.
Okay. So now let us go to the second part of the question. So calculate the exit gradient if the average length of the last field is 0.9. Alright. So how do you calculate exit gradient? Any idea? I exit. How do you calculate I exit?
It loss per drop upon length of the
Delta H divided by length of the last element, right? L exit. So for that we need to find delta H. How will you calculate delta H? H by N. NF or ND?
ND.
How much you are getting? 14 by 12.
1.167.
1.167 meters. So what is I exit? Exit is equal to 1.167
1.2967.
0.9.
2967.
1.296. Okay. All right. So that is one thing. And second is we need to calculate the critical hydraulic gradient. So let me erase some points. I will put a new slide. Just so What was the I exit? I exit was 1.296. So we need to calculate IC. What is IC? How IC is defined? What is the relation? Am I audible? Hello?
Yes, sir.
What is the
Audible.
relation of relation of IC? Do you remember or not?
No, sir. It was explained. Right.
G minus 1 by
On a specific volume.
1 plus E. So calculate. You have been given specific gravity and you have been given void ratio. How much you are getting?
E कितना है सर? E वैल्यू
Question में है ना? Yeah. 0.56 and G is 2.65.
1.057. 1.057.
BC is 1.057.
057.
Right. So what is the last part of the question? Comment on the what is the last part? Comment on the
Stability of the
how
river
will you
bed.
comment on the stability?
Both the point check IC and IE.
What should be it?
IC is 1.057 or I.
How will you what is the parameter for checking the stability?
If IC is greater than IE तो safe और IC in IE is मतलब less तो unsafe for the river bed.
What is the exact parameter? It is factor of safety, which is given as IC by
IE.
I exit should be greater than 1. So calculate the factor of safety. 1.057 divided by 1.296. Is it greater than 1 or less than 1?
Less than 1.
So then what about the stability?
Is
Is the dam stable or not?
not unsafe.
So the dam is not stable. All right. Any doubts?
No, sir.
Okay. So let us take a short break. We will be back by 6:05. All right. So I will also. There is a small emergency. I will be right back.
Okay, sir.
Okay, shall we start? Hello? Shall we start?
Yes.
Now, what we'll do is we'll solve this question now. All right. So, this is a dam that has been given to us, and the cross section of the dam is given to us. All right.
Sir.
Okay. Now, what we are being asked to do is we need to calculate the uplift pressures. What is uplift pressure? What is the other term for uplift pressure? What is uplift pressure? Any idea?
और वाटर प्रेशर जो अब
Yeah. So this is uplift pressure is nothing but pore water pressure. So what is pore water pressure?
Pressure between walls of
So, so if you come to the Bernoulli's theorem, total head is divided into how much? Total head is
pressure head plus kinetic head or
elevation head plus
kinetic head plus that term elevation head.
pressure head. Kinetic head is neglected because the velocity is very small, right? So the total head in this is elevation head and pressure head. So pore water pressure is related to which head?
Elevation.
Elevation. What does water and elevation has to do? Pore water pressure is nothing but pressure head. Okay.
Okay, sir.
So that means we have to calculate what at every point. There
Pressure
are
is
A, B, C, D, E, and F. We need to calculate pressure head at A, B, C, D, E, and F. All right. Any doubts?
no, sir.
Now, what is the head difference here? H is equal to
8 meter.
8 head difference.
Difference 8 minus 2.
It is 6 meters. This upstream minus downstream head, which is 6 meters. Understood?
Yes, sir.
Now, how many drops are there from the upstream to downstream end?
Drops. Normal pressure drops.
What is
Drops.
ND?
D is 7.
7, right? ND is 7. So, pressure head is defined as, what is the relation of pressure head? Delta H into
Delta H into unit
sorry,
weight.
pressure head is delta H, right? So then pore water pressure is defined as delta H into, how will you convert head into pressure?
Head into pressure.
Hmm? How will you convert the head into pressure?
Pressure.
Will you convert head into pressure?
Rho G into H.
Rho G into H. So you have H. Rho into G is defined
Gamma.
as what?
Unit weight of that fluid.
Unit weight of that fluid. which is gamma W. Assume gamma W as 10 kilonewton per meter cube.
Okay, sir.
Okay. Now what is delta H? Delta H is equal to
For water pressure upon unit.
delta H from here,
So given 6.
H by ND,
Okay.
6 by 7. How much we are getting?
0.857.
0.857,
857.
or you can take it as 0.86.
तो 8.6 आ जाएगा for water pressure.
Wait, slowly, you do slowly. So now what happens? You have to calculate at each point, right? Just a minute. சொல்றா.
என்ன எப்ப போகலாம் விளையாட?
போலாம், நான் ரூம்ல தான் இருக்கேன்.
ரூம்ல தான் இருக்கிறீங்க? அப்ப நீ நேரத்திலே போயிட்டு வந்துடலாமா?
எத்தனை மணிக்கு போலான்னு சொல்லு.
நான் சிவன் கூட பேசி கூப்பிடுறேன். ஒரு 7 மணிக்கு போயிடலாம்.
7:15 போலாம்.
ஓ, அப்படி வேற இருக்கா? ராகு காலம் முடிஞ்சுச்சா? இளைய காலத்து
ராவு காலம் இல்லடா, NPTEL செஷன்ல இருக்கேன், அதனால.
கேது வருது, அதான் கேட்டேன்.
அதாவது NPTEL செஷன்ல இருக்கேன். சரி, அதான் வந்து
என்ன ஸ்டூடெண்ட்ஸ் இது எப்ப முடியும் உனக்கு?
அதான்டா 7 மணிக்கு முடிஞ்சும்டா, 7:15 போலாம்.
சரி, எனக்கு ஒரு டவுட் இருக்குது. நான் ஆன்லைன்ல இருந்து கேட்க போறேன்.
லிங்கே இல்ல, எப்படி வருவேன்?
அதெல்லாம் நான் கண்டுபிடிச்சு வந்துடுவேன்.
சரி, ஓகே.
ஓகே சார். தேங்க்யூ சார். வைக்கிறேன் சார்.
Sorry. So you have to calculate pressure head at each point, right?
Okay,
So
sir.
what will be the pressure head at A? See, this is the head loss, right? Actually, there is a small mistake here. So this will be, sorry. So pore water pressure will be pressure head, right? Pressure head will be total head difference minus N into delta H. Okay. So
Okay.
what happens is total head loss is 6 meters.
Yes.
So minus, so for point A, what will be the, there is only one drop, right?
Yes, sir.
So 1 into head loss is 0.86. Sorry, this is going to be 88. So see, are you understanding what I'm saying? So if you take at the first point, the head is going to be 8 meters, right?
Yes, sir.
So, and at the first drop, it is going to be 1 into the head loss. For one drop, the head loss is 0.86.
Yes, sir.
So what will be the pressure at 8 minus 0.86? It's going to be 7.14.
Oh,
So pressure at uplift pressure at A is going to be 71.4 kPa, right? So similarly, calculate for B, C, D, and D, E, and F, and let me know. What will be for B? PB is equal to 8 minus
right.
2 into 0.86 into
6.28.
10.
10.
Uh,
62.8
62.8
kPa. 8 kPa.
kPa. At C,
let's see, 54.2 kPa.
54.2 kPa. And D
45.6 kPa.
6 kPa. And C, sorry, E
37 kPa.
37 kPa. And F is
28.4 kPa.
28.4 kPa. So just you have to reduce 8.6 kPa 6 times. All right, understood?
Yes, sir.
Any doubts?
No, sir.
Okay. Shall we go to the next question?
Yes, sir.
Let's move to the next question. So derivations we will see. If we have, we'll solve this question, and if we have time, we will see the derivation. All right. So now right. So now this is the diagram that is given. Right. Refer to the earth dam shown in figure below. Given details are beta is 45 degrees, alpha is 30 degrees, B is 3.33 meters, H is 6.6 meters, height of the dam is 8.3 meters, and permeability is K, that is 2 into 10 power minus 4 centimeter per second. So we have to calculate the seepage rate at the downstream end. All right. Any doubts?
No, sir.
So this conditions. So how there are two formulas, two relationships. So I will be writing. So first is to calculate the seepage rate, Q is equal to permeability into L sin alpha into tan alpha, right?
Yes, sir.
So in this we know alpha, we know sin alpha, tan alpha, K we know, but the unknown parameter is what? L, right? L is the distance between the toe of the dam to the outcrop point, which is given by the relation d by cos alpha minus
Root under d square
root
upon
over b square by cos square alpha
minus h square upon
minus
h
h
square
square by sin
and
square
alpha.
alpha, right? Now in this, what are all the parameters which are known? Alpha we know, which is 30 degrees, right?
Yes, sir.
B we don't know, right?
Yes,
H
sir.
we know, H is how much? 6.6
6 meter.
meters. Now how to calculate D? So D, for this we need to carefully observe the figure. So there are two parts here. So let this be X and let this be Y. Alright.
Yes, sir.
Now D is going to be 0.3 into delta plus
X
X plus
plus b
B plus
plus y.
Y. Alright. Now
Yes.
in this, what are all the parameters which are known? We know only B, right?
Yes, sir.
B is 3.3 meters. Now what we need to calculate is, we need to calculate delta. So from triangle, this triangle, right? What we know,
Beta is given
H
and
by delta is equal to tan
alpha
beta,
beta beta.
right? So beta we know, beta is 45 degrees and delta is how much? Delta is equal to h. So delta is equal to 6.6 meters. Understood? Tan 45 is 1, right?
Yes, sir. Yes, sir.
Now we need to calculate x. How will you calculate x? Same thing.
Same.
Know this, right?
Yes, sir.
Let us take this bigger triangle.
8.3 is given.
We know the height
8.3.
and this is going to be x, right?
Yes, sir.
So same thing, tan beta is equal to 8.3 divided by delta plus x. So tan beta is 1, 8.3 is equal to delta is 6.6 plus x. X is going to be how much?
1.7.
1.7 meters. Now the last parameter which we don't know is y.
Y.
So how will you calculate y? Let us take
Tan alpha is equal to 8
this
point.
triangle,
Yes.
right? Or we can take this also. Or we can take this. This is going to be y, right?
Yes, sir.
And this is going to be total h. So tan alpha is equal to
14.37.
8.3 by y.
Tan
Y is equal to
14.
8.3 divided by
Tan 30.
tan 30. How much you are getting?
14.37.
14.37
37.
meters, right? Any doubts?
No, sir.
How much is d now? D is equal to all the things we know. 0.3 into
6.6.
6.6 plus x is 1.7 plus b is 3.3 plus y is 14.37.
14.37.
How much you are getting? Ten point 3.3,
20
17.67,
20.37. 20.35
1.35 meters,
meter.
right? Now you calculate L.
D upon 4. Three 3.83 length is given. मतलब calculation पर 3.3 3.83
3.83.
83.
3.83 meters, right?
Yes, sir.
So what will be Q now?
Yes.
Use the units properly.
Two point two one into 10 to the power minus 6 meter cube per second
0.21
into 10 to the power minus 6 meter cube per second.
6 meter cube per second. How much per day? Liters per day?
191 liter per day.
191 liters per day. Are you getting the feel of how much water is getting wasted? Huh?
191.
Yeah. So are you able to imagine the amount of water that is getting wasted per day due to this earthen dam construction?
Yes.
All right. So any doubts?
Yes, sir.
So we have some around 20 minutes time. So we will see some derivations. Right.
Okay, sir.
So derive the expression for effective permeability for anisotropic soils. So how will you do it? So first, anisotropic soils. What do you mean by anisotropic soils? What do you mean by permeability anisotropy? Any idea?
Yes, sir. Isotropic यानी one point पे all direction में same, but
Anisotropy is consider a two-dimensional system. So what does isotropy mean and what does anisotropy mean? And this anisotropy is usually in this context it is for permeability. What does this permeability anisotropy mean?
यानी permeability in all direction मतलब isotropic अगर है तो सभी डायरेक्शन में सेम रहेगा, बट anisotropic में सभी डायरेक्शन में सेम नहीं रहेगा.
Same नहीं रहेगा. So it is a two-dimensional. If we consider a two-dimensional system, let us consider a two-dimensional like a small block, right, of dimension dx, dz, right? So it has a permeability kx, vertical permeability ky, right?
Yes, sir.
So now what we have to do is we need to calculate effective permeability, right? Effective permeability means we have to make some changes such that what we achieve is that kx is equal to ky. That is, make some changes that leads to kx equal to ky is equal to k effective, right? So usually what we do is we change the dimension of this element, right? We define a new element which is known as effective element of dimension dx dash, but depth remains same dz, such that permeability becomes Ke and Ke. Understood?
Yes, sir.
Okay. And the amount of fluid that is passing through this element is defined as Q1, and this element is defined as Q dash, right? So what is the condition? The condition needs to be Q1 is equal to Q dash, right?
That's
So now the cross-sectional area is going to remain same, this cross-sectional area. That means you consider the element with of into the plane of the screen as one unit. So the cross-sectional area of the flow of fluid is going to be same, right? The length is going to be different. Understood?
yes, sir.
So that means Q is defined as K into, how will you define it? Dou H by dou X Kx
Into
is equal to Ke into dou H by dou X dash, right?
yes.
Now Kz into dou H by dou Z is, or otherwise we have changed just the X direction, right?
Sir.
So, or we will do one thing. So for this you need to so we will keep this presently. So to solve this, you need to understand the relation between H dash and X. All right. So we will come back again. So we will derive this first, and then we will come back to it. All right.
Okay, sir.
So I should have done this properly. So sorry for the confusion. So now this is the question. This is the derivation. Prove the relationship of the flow net dimension through an interface of a non-homogeneous section, right?
Okay, sir.
So non-homogeneous section, how will you define the non-homogeneous section? So now this is the flow net, right?
Yes, sir.
This is going to be the flow net. Let this be the dz and let this be dx. All right.
Yes, sir.
And flow nets are, what is the fundamental property of flow nets? They are elementary squares, right?
Yes, sir.
So that means, sorry, uh, so we can rectilinear it. So let this be dx and let this be dz. and what we do is we will name the corners. So A, B, C, and D. So let this be the element, right? So now what we'll do, this, the water flows both in this direction. It comes out of this section in this, like this, and
Yeah.
this direction. Both two-dimensional flow. Understood?
Yes, sir.
So now the permeability along x direction be kx and kz. All right.
Yes, sir.
And what about I? Ix is equal to minus dou h by dou x. So Iz is equal to minus dou h by
Yes, sir.
dou z, because the water is losing its energy, right? So
Yes,
that's
sir.
why it is negative. Any doubts?
No, sir.
Now what we need to do is we need to do the Darcy's law. So Vx is equal to kx into minus
D.
kx into dou h by
Yes.
dou x. Vz is equal to minus kz into dou h by
Yes.
dou z, right? So now if we consider this, this is Vx and Vz. Now what about Qx? That is not Qx, it will be what will be the fluid that is entering into in the phase AB, this phase. QAB is equal to Vx into dz into dy, which is into the plane. Are you getting?
Okay, sir.
Any doubts?
सर क्यों ए में फिर से एक बार एक्सप्लेन कर दीजिए कैसे है?
See, this, when if I consider it as a three-dimensional system, right?
Okay. Yes.
So this is going to be x, this dx, dz, and
Yes.
dy.
Right.
So what we are trying to do is we are trying to, so water is flowing from here and water is flowing from here, right? Or you can consider it as one also. That is not an issue. All right.
Okay, sir.
Now, what about Q? Q is velocity into area, right? Cross-sectional area. So
Yes.
what the discharge through the face AB is what? The velocity is Vx, and the cross-sectional area is dz into dy, right?
Yes, sir.
And similarly for the water enters in the phase CB or BC, so QBC is equal to Vz into dx into dy,
Okay.
right? So now we have calculated the amount of fluid that is entering into AB. So we need to calculate. Second is how much it is entering out of CD. Usually, what happens is as a, what to say, as a universal rule, we we uh, uh, we we take that some of the fluid is lost during this process. That can be zero also, but for the derivation, for the purpose of derivation, we understand that some amount of energy is added or subtracted from the fluid. So what we do is the exit part we add a term which can be positive or negative, right? So dx dy plus what happens it at the exit dou vx into dou x by dou x into dx into dz into dy, right?
Yes.
So similarly for QAD it will be vz into dx dy plus dou vz by dou z into dz into dx into dy.
D.
All right.
Yes, sir.
So now ideally what should happen? QAB is equal to QCD, right?
Yes, sir.
Sorry, the total, that is the total amount of flow should remain constant. So the total inflow is going to be total outflow. So what happens is total inflow is how much? QAB plus in this direction what is the QVC
Yes.
is equal to
QCD.
QCD. Just a minute. There is a small this one. Total inflow is equal to total outflow, right? Right, that is it. So now QCD plus
QAD.
QAD, right? So now what happens? So QAB is Vx into dz dy
Into D.
plus Vz into
DX.
dx into dy is equal to QCD is going to be Vx into dz dy plus dou Vx by dou x into
DX.
dx dy.
DZ.
Understood?
Yes, sir.
Plus Vz into
DX.
dx dy
Dot.
plus dou Vz by dou z into dz dx dy.
D.
Understood? So now what happens? This get cancelled, this get cancelled, this get cancelled, this get cancelled, right? Now this part, this volume is also going to get cancelled. When you bring this, when you take this as common, what happens? So it is going to be dou v x by dou x plus dou v z into dou z is equal to 0, right? So this dx dy dz will, when it goes to the other side, it becomes 0, right? Any doubt? Hello?
Yes, sir.
Any doubts?
No, sir.
Now we have to convert in terms of head. So how it is defined? Dou by, let me put it in a new slide. Are you understanding till now, or you are facing any difficulties?
No, sir.
Okay. Now what we have is dou vx by dou x plus dou vz by dou z is equal to 0, right?
Yes.
So we know that Vx is equal to minus Kx into dou h by dou x,
Yes.
right?
Yes.
So Vz is equal to minus Kz into
One.
dou h by dou z, right? we substitute here, what we will get? Minus is common, so minus will be taken out. So we will get kx into dou square h by dou x square plus kz into dou square h by dou z square is equal to 0, right? Understood?
Yes, sir.
Now, if it is an isotropic system, what is the condition? It is going to be kx equal to ky, right?
Yes, sir. All the direction should be.
So then what will happen to this equation? Dou square h by dou x square plus dou square h by dou z square is equal to 0. So
Yes.
what is this equation known as? This equation is known as Laplace equation, right?
Yes.
Now you are understanding how this equation is derived. Now the second part is if it is an anisotropic system, what will happen? So what we will do is we will take this dou square h by dou x square. We will take kz outside. All right. So what will happen? Kx by kz, right?
Yes, sir.
Plus dou square h by dou z square is equal to 0. All right. So now what we will do is, let us take this to the denominator. Dou into root over kz by kx into x whole square plus dou square h by dou z square is equal to 0. Understood?
Yes, sir.
Now let us define this as x dash. So if there is an anisotropic system, so we have to if you have a dam section, right, like this, right? So when you have a dam section like this of height z and length x, right? So and the permeability is it has an anisotropic permeability. So what we have to do is we need to change this cross section of the dam such that it becomes x dash and the height remains z. So that x dash is defined as root over kz by
KX.
kx into x. All right.
Yes.
Any doubts?
No, sir.
So this is the relation. All right. Now we will understand the next part of the derivation, which is the effective permeability derivation,
Yes, sir.
right? So now this is where we left. Here we left here, right? So
Yes.
we need dx dash. So what we'll do is kx into dou h by dou x is equal to ke into dou h by dou into root over
KX.
kz by
KX.
kx into
X.
x, right? So now if we equate it, so what is going to happen? So everything is going to cancel out. Kx is equal to ke divided by root over kz by
KX.
kx, right? Understood?
Yes, sir.
Now what happens to ke? Ke is equal to kx into root over kz by
KX.
kx. which is defined, then if we simplify it, we get Ke is equal to root
Okay.
over Kx into Kz. So this is how the effective permeability is derived. So it is a geometric mean of horizontal and vertical permeability. Any doubts?
No, sir.
So with this, the session comes to an end. So now I would like to get your feedback. How was the session? Where can I improve? How did you find this session? Can you give your feedback?
सर 5 गुड सर बहुत अच्छा
Yeah, I am unable to understand.
सर बहुत अच्छा था सर
You were able to understand my flow and these things. The speed was right. Speed.
is great and
Okay. So just a minute.
sir can you share if this folder is any जगह
Yeah, the slides will be shared with you. That is not an issue. Slides and video will be uploaded, and the links will be shared with you. So you can go through anytime. So of all the weeks, in fact, you can go through all the weeks videos, problem solving session videos, and you can due to time constraints, there might be some questions which are unsolved in the previous weeks also. So you can, since the slides are getting uploaded, you can also go through those questions and try to solve it. So if we have some extra sessions, we will try to conduct and cover those questions. All right.
okay sir.
So with this, this was a relatively shorter week, I think. So we had to uh, stretch a bit with the limited scope we had. So I hope the entire content of the week has been covered, right? So with this, I would like to conclude the session, and as a concluding remark, so these sessions will be held every Saturdays from 5 p.m. to 7 p.m. unless otherwise informed. So it is now there are barely 3 sessions left. So please try to attend the sessions regularly and please be in time.
Okay, sir.
Uh, and the primary requirement is watch the lectures of that particular week before attending this session so that you do not get confused or you don't you don't feel alienated to it. All right.
Okay,
So the following 3 weeks will be, one is the external loadings, analysis of external loads on the soils, followed by settlement behavior, and last one is time rate of consolidation. So these 3 weeks will cover these 3 topics, which are utmost important for uh, geotechnical engineering and further for foundation engineering also. All right. So with this, I request you to attend these sessions at least from here after regularly, and that's all. Thank you.
thank you, sir.
I'm sharing my screen and I'm closing the meeting, so you can leave. Thank you.